Hi class, in this video we're going to talk about 3.2. We're going to look at another tool for finding derivatives. This tool is called implicit differentiation. So first of all, we have to know what it means for a function to be defined explicitly versus implicitly. So explicitly, what I want you guys to think of, what this means is, can we rewrite y in terms of x, which means like y equals something with x, okay? So if we can do this, it is explicitly defined, okay? If we can't, then we say it's implicitly defined. So for example, can we get y by itself here and rewrite this as y equals? Well, yeah, we could subtract the x squared and then take the cube root, right? So we'd get the cube root of 8 minus x squared, right? We can get y by itself there. Here, I could divide both sides by x, right? So these both are yes. Yes. Which of the following, which of the following is not really yes. Which of the following can be defined explicitly? So for sure, 1 and 2 can be defined explicitly. Okay, here, to get y by itself, notice I have y in like multiple terms. So if I like move these two terms to the other side, I have y on both sides, so taking the cube root, I don't get y by itself. So this one is no. We are not able to get just a single y term and then y equals. This one, as well, we can't because we have a y attached to the cosine and this 3. Because I could do cosine inverse of both sides, but I still have this y over here. So this is another one that we cannot define explicitly. This one we can, right? To get rid of natural log, we would exponentiate both sides, right, to get rid of the natural log. So we get y equals e raised to the x squared minus 3x. So this one we can define explicitly. This one may seem like no because I have y in multiple terms, but I could factor out this y and then get y by itself. So this one we actually can as well define explicitly. So as long as we can get y by itself, we are able to define it explicitly. Okay, so we know how to take the derivatives of these things, right? We can use our power rule, we might have to use the chain rule, but for implicitly defined, so ones that I cannot get y by itself, we're still trying to find dy dx, right? But we're going to use implicit differentiation. And so what we're going to do is we're going to differentiate both sides implicitly, define function with respect to x. So I want to point out two pieces of information here. The derivative of x with respect to x, we don't really use this very often because it's kind of like duh, but the derivative of x with respect to x is dx dx, which anything divided by itself is 1, right? So the derivative of x is 1, right? We've been doing this consistently. Now, something else we've been doing, but it's going to look slightly different because it's going to be inside of an equation, but the derivative of y with respect to x is dy dx. Or we've been using y prime a lot. Same thing. So these are two things we've already been doing. The difference is our dy dx is going to be like in the equation, and then we're going to have to get it by itself. So here's what I want you guys to think of. We are going to find the derivative of this expression. So these are the number 3 and 4 that we could not define explicitly. So we're going to use implicit differentiation. So what I'm going to do is I'm going to differentiate. Okay, so if it's with respect to x, right, we're just going to differentiate like we normally do. So this is going to be bring down the 4, multiply by the 3. Oh, 12, excuse me. 12 x to the third. And technically I could put a dx dx here, but dx dx is 1, right? So I am not going to add that piece. Okay, now this part, this is a product. So I'm going to put a minus, and then I'm just going to do the product rule inside here. Okay, so the derivative of x is 1 times the second piece, as is, plus derivative of x as is, times the derivative of y. So this is where the derivative of y is dy dx. okay? Then plus y, so there's our product rule, plus y cubed. So I do have to use the power rule here, so it's 3y squared, but again, it's with respect to y, so we always have to tack on the dy dx. Derivative of a constant is 0. So what I'm going to do here, you guys, is our goal then is to solve for dy dx. So I want to like rearrange this, and I want to get dy dx equals something. So I'm going to simplify here a little bit. So we've got, let's see, 12x cubed minus y plus x dy dx plus 3y squared dy dx equals 0. Okay, so I'm going to move these two pieces over. So I've got x dy dx plus 3y squared dy dx equals, so I'm subtracting that 12x cubed and then adding the y. Okay? And now I want to get dy dx by itself, so I'm going to factor it out. So dy dx times x plus 3y squared equals negative 12x plus y. And then, sorry, I got to come back up here. So then I can divide both sides by x plus 3y squared. So I've got dy dx equals negative, oh, sorry, I lost my cube there. Negative 12x cubed plus y over x plus 3y squared. So we, remember, dy dx is like y prime. We solved for that, got dy dx by itself. There is our derivative with respect to x. Okay, let's try this one. So we're going to differentiate both sides. Anytime I'm doing it with respect to y, I have to include the dy dx. Okay, so derivative cosine is negative sine, and again, it's with respect to y, so I have to tack on the dy dx. Equals, derivative of 3x is 3. It's with respect to x, so again, you can put the dx, but it's more writing that you don't have to do. Plus 3y, so plus 3, but it's with respect to y, so dy dx. Okay, so I need the dy dx's on one side, and then I'm going to factor it out to get it by itself. So I'm going to add the sign over here and subtract the 3 over here. So we've got negative 3 equals sine y dy dx plus 3 dy dx. Factor out the dy dx. So I've got sine y plus 3 dy dx, and then divide to get dy dx by itself. So we got sine of y plus 3 equals dy dx. Okay. Number 3, express as a function of x alone. Okay, so what this means is you guys can see we've got y's in my derivative. I have x's and y's, so this is saying use only x's. Well, we're going to, in other words, do some substitution here at the end. Okay, remember, this is really tangent of y squared. So I'm going to differentiate here. Derivative of, I got to use the chain rule, so I'm going to bring down my 2. So we've got 2 tangent of y now to the 1, right? But by the chain rule, now times the derivative of tangent, which is secant squared, y, and this whole time it's been with y's, so I have to do dy dx. Derivative of e to the x is itself, and then again, you don't have to put the dx. Okay, so now solve for dy dx. So I'm going to divide by this whole thing. So we've got dy dx equals e to the x over 2 tangent of y secant squared y. Okay, so we would be satisfied with this answer, but because of this direction, we need to rewrite we need to rewrite these y's using x's. So what I'm going to do is I'm going to go back to the original equation and see if we can rewrite that in terms of x. Okay, so here we've got tangent squared of y equals e to the x. So what I'm going to do first is I'm going to get rid of the squaring by taking the square root, which is the same as multiplying by the applying the 1/2 power. So then I've got tangent of y equals e to the x over 2. Okay, and then tangent of y is equal to this, so I can put that in for tangent of y. Okay, so one other thing that's helpful here is we have a Pythagorean identity that says 1 plus tangent squared equals secant squared. So I am going to remember this is the same as e to the x based on our original equation. So 1 plus e to the x is the same as secant squared. So again, I'm going to replace this with the secant squared. So now we have dy dx equals e to the x over 2, instead of tangent of y, we're going to replace it with this, e to the x over 2. Instead of secant squared y, we're going to replace it with 1 plus e to the x. So that is our derivative written as a function of x alone. And we only had to do that, again, because of that specific direction. Okay, number 4, we got just a couple more here. Find the equation of the tangent line to the graph of the ellipse at the point here. Okay, so equation of tangent lines we know is going to involve the derivative and then plugging in the x value to find the slope. Now, ellipses, you guys did some conics in Algebra 2 and Pre-Calc, so these are ones that cannot be explicitly defined. So we are going to use implicit differentiation. So we're going to differentiate, so we're going to use our power rule, so I've got 6x plus 8y, but it's got a y, so we got dy dx equals 2. I'm going to solve for dy dx, so I'm going to subtract the 6x and then divide by 8y, so we got dy dx equals 2 minus 6x over 8y. Notice all those can be divided by 2. I'm going to do that just because it's smaller numbers to work with. All right, so we just reduce the fraction is all. Okay, so our slope, right, that's what I need to write the equation, right? The equation of the tangent line, we're going to use point slope. So what we're doing right now is we're trying to find the slope. So the slope of the tangent line, right, is this at this point. So because my derivative involved x and y, we need to use the x and the y coordinate. So I'm going to plug in 1 minus 3 for the x coordinate, we're plugging in a half, and then 4 times the y coordinate, negative a fourth. All right, when I simplify this, let's see, we get 1 minus 3 halves is 1 minus 3 halves negative a half over negative 1. I think we get 1 half there, right? Is that right? 1 half, yep, negative a half over negative 1. Okay, so there's our slope. So now y minus our y coordinate, so plus a fourth, equals our slope of 1 half times x minus, oh, losing my lead there, x minus the x coordinate. So there's the equation of the tangent line. Okay, number 5. Now we're going to find a second derivative using implicit differentiation. Okay, so we're finding y double prime expressed in terms of x and y. Okay, so we're going to start the same way. We got to find the first derivative first. So I'm going to do 2y using the power rule, but got to include dy dx minus 2x equals 0. Okay, so what I'm going to do is I'm going to do the same thing I've been doing before. I'm going to get dy dx by itself. So I'm going to add the 2x and then divide by 2y. So 2x over 2y, those 2's can cancel, so dy dx equals x over y. And remember, that's the same as saying y to the first, right? Or, excuse me, y prime first derivative. So, basically, I know the first derivative equals x over y. Okay, so to find the second derivative, I have to do the quotient rule here. So y double prime, or remember that can be written like this, over, oh, sorry, that should be a y. This is Leibniz notation, okay? So it's saying we're finding the second derivative again with respect to x. So that's why the squared's on the x, or the 2's on the x. Okay, so we're going to do the quotient rule. All right, so my numerator is x, so derivative of x is 1, times the denominator minus the numerator as is, times the derivative of the denominator, which is dy dx, over the denominator squared, okay? Okay, so typically, guys, we won't leave dy dx in the expression because we already have something that dy dx equals, right? dy dx equals x over y. So we're going to replace that. So we're going to say y, right, 1 times y is y, minus x times x over y, over y squared. And I'm just going to simplify just a little bit here. So I've got y minus x squared over y squared. I don't love the fraction and a fraction, so I'm going to get a common denominator here. So we have multiply this guy by y, so I've got y squared minus x squared over y squared. Remember, dividing by a fraction is the same as multiplying by its reciprocal. Sorry, I'm going to come back this way. So we've got y squared minus x squared over y times the reciprocal of this, 1 over y squared. So here's our kind of more simplified looking expression, y squared minus x squared over y cubed. And that would be our y double prime. Oh, I'm sorry, I was looking at my notes, I went one more step. Okay, so this is y double prime, but notice this guy's right here came from up above. So y squared minus x squared is equal to 5. So we actually could even write it like this, 5 over y cubed. So there's our second derivative. All right, last example. Which of the following is true about the curve given by this expression and the point 2, 1? Okay. All right, well, we can see all of these are talking about the tangent, so that's going to involve the derivative. So I'm going to go ahead and find the derivative and plug in these values to see what we know. Okay, so I'm going to use implicit differentiation because I cannot get y just by itself here. So I'm going to differentiate here. So we got 2x minus, this is a product. So we've got 1y plus x dy dx plus 2y dy dx equals 0. Let's get dy dx by itself. So 2x minus y, and really this is like a -1 distributing, so we've got minus x dy dx plus 2y dy dx equals 0. Okay, so what I'm going to do is I'm going to factor out the dy dx and move these to the other side. So we've got dy dx, we've got a -x, positive 2y left with those. We're moving the y, we're subtracting the 2x. Okay, and then divide here. So we got dy dx equals y minus 2x over -x plus 2y. All right, so there's our slope, and then we want to know at the point 2, 1, what's happening. Okay, so if I plug in 2 for the x and 1 for the y, so we got 1 minus 2 times 2 over -2 plus 2 times 1. All right, so here I get 1 minus 4, -3. Here I got -2 plus 2 is 0. So because we're getting division by 0, we have undefined at this point. So our tangent line is, we have a vertical tangent line is what that means. So dy dx does not exist, and the tangent line is vertical. That is the option that is true based on what we found about the derivative and the slope of the tangent line. All right, that's it for 3.2. Thanks for watching.